So what happens to a material if we load it into the plastic region? Now I know in the elastic region, once I let go, I am going to have that elastic strain go away. Once I get into the plastic range, some of the strain will go away, but not all of it. So you are going to have some recovery. You're going to have some of what is called the elastic recovery. So let's look at this little graph that I've got here. And once again, this looks probably like an aluminum. I'm going up here into the plastic region. So the linear elastic region probably I'd say ends about right here. Because that's, let me redraw that. Ends probably about right there. Because that's where it stops really being linear. So this entire thing right here, this is all plastic deformation. So plastic deformation means I am completely changing the atomic structure of the material. So what happens? Let's draw a straight line down here. So this is the strain rating I'm at. We'll call that E because it's not on here. So you let go of the material and something does happen. You see, I'm drawing this line from C to D, has the same slope of E as the linear elastic part A to B has. So what I'm going to do is I'm going to draw this line back, the same slope, coming back to this point D. Now, what I have here is from D to E, so D to E, I believe that's the symbol for a line segment. D to E is what's called the elastic recovery. So that is what we've recovered strain-wise from the plastic deformation. Now, if I look here from A to D, though, A to D is what we call the permanent set. This is what we've changed the material completely to. So that is the amount of strain that we've permanently put into the material, and we've permanently changed the material. In fact, once we add permanent set to a material, and this would happen if you do strain hardening, you would actually develop a new stress-strain curve from this point. And basically what it would do is it would come out here, and it would go and off and do whatever it's going to do. So permanent set is actually a combination of two different parts, and we just showed you the first part. So the first part is what's called that stress-dependent part. So this is what we've put in with the stress that we were just pulling, and that is called slip. We have the second one that is a time-dependent part. And so this is from another phenomenon that I will actually talk about here in a second. And we're going to call this creep. And creep comes from one of two places. You can either have fatigue or you can have temperature creep. Sorry, temperature creep. So this is what happens when we plastically load a material. Okay. So that's the slip part of this. Let's talk about the creep part. So materials that are subjected to repeated cycles of stress strain cause the structure to work. The same way that by pulling it into the hardening region, we're working the material. Well, we can work the material using these low-level stresses of repeated cycles. And we can either do that by stress, by actually grabbing on it and yanking it and cycling it back and forth, or we can do the same thing with temperature, because we'll talk a lot about temperature later in the class. But as we heat and cool things up, we'll do the same thing. It'll lengthen and shorten, lengthen and shorten. And so what that does is it causes the microscopic features where those localized stresses are, and it causes, we're going to start to get much greater than average stress. Eventually, the material, even if it's ductile, becomes brittle. And this is a problem because eventually a brittle material can lead to failure, because what's the difference between a brittle and a ductile material? Ductile material can plastically deform, a brittle one cannot. And so if you work this through either a cycling process with stress or with a temperature process, what may happen is the ultimate stress, or the yield stress of the material, will come down so low that when it was designed, the application was fine, But now after running it through 10 million cycles, all of a sudden, the stress value is a lot lower. So what do we do? How do we account for that? Well, we can mitigate it by keeping the stresses below what the fatigue limit of the material is going to be. Now the question is, how do we know what the fatigue limit is? Well, we can find the fatigue limit of a material by looking at what's known as an SN curve. SN means S is for stress, N is for number of cycles. And so what we have here is, this is one that we have two different materials on. We have a grade 50 steel and we have an aluminum. Now, these charts are going to be what's known as semi-logarithmic. So over here on the y-axis, we have stress in KSI, and that's the yield stress of the material. And then down here along the x-axis, we have number of cycles, and this is what's in the logarithmic scale, which is why it's semi-logarithmic. And so basically, every time that we hit 10, we go up by an order of magnitude. 10 to the third, 10 to the fourth, 10 to the fifth, da 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 da. This is so we can deal with mass numbers of cycles. So what do I do with this? Well, if I'm only looking at 10,000 cycles here at 10 to the 4, well, aluminum, which is normally about 40, this aluminum is normally about 45-ish KSI yield strength, we can sit there and go, well, if I'm going to cycle it 10,000 times, it's probably going to drop down to about 43. Because I just look at where it crosses, yeah, it's probably 42, 43. If I look at my grade 50 steel, which is normally around a yield strength of, it looks like 47, if I go, and it starts at 10,000, so it's about 47. Okay, so what if I have an application where this is cycling, and I'm going 100,000 times, 10 to the 6, and I design my device to yield, we put a factor of safety of maybe 1, let's say 1.5 in, and so 35 is what it's designed for. I go to 100,000 and I will see with my aluminum, well, my yield strength is only going to be about 25. And so what happens? Well, that means as this aluminum's going, once I get past 35, somewhere around, getting close to 10,000 cycles. Is that right? Sorry, 10 to the 5. I'm not thinking this morning. 1, 2, 3, 4, 5. Actually, 10 to the 5 is 100,000 cycles. 10 to the 6 would be 1,000,000. So I'm not really thinking this morning. That's what you get for recording early in the morning. But anyway, but once we get up to those number of cycles, what happens is it's going to break down. If my thing is 35, once I hit 10 to the, let's see, that's 10. So we're looking at 1, 2, 3, 4, 5, 6, 7. Once we hit 7 times 10 to the 4 cycles, it's gonna break down. It's gonna be a problem. So if you know the number of cycles that you're going to run, you can design things better. If I know this thing's got a useful life of 10 to the 6 cycles, then I got to make sure that I design not using the 46 yield strength in mind. I got to use the 25. Now this is an important concept because a lot of times you're designing machines that are going to have a lot of moving parts. And so if you think about one of the airplane engines get overhauled every so many hundred of hours because of things like this, because we want to make sure that we're not stressing the thing, because something fails in an engine airplane, it's usually a bad time because you're flying. Excuse me. I've done this in my own career. I was investigating why something was breaking because they took a mirror that they had in a scanner, like at the grocery store, and they couldn't understand why the new one was breaking because they've had the old one for years and it never had a problem. Well, what the engineers had done is they just scaled it up by twice, and they never even thought of looking at what the fatigue limits were. And after about 100 hours of operation, it was passing the fatigue limit because they made it twice as big, put a lot more stress on it, and the things were disintegrating. It's kind of funny, but we figured it out. They asked me, because I was an analyst at the time, they're like, okay, what's going on? I did the stress thing, and they're like, oh, see, they're telling me the stress is fine. And I was like, yeah, but you didn't take into account the fatigue. One last thing to note about the fatigue is you'll see with the steel. especially we hit some point where it flattens out here. What's going on? That's what's called the endurance limit. So on a lot of materials, especially steel, you can only work it so much and then it's not going to matter. So once the steel gets worked down to 10 to the 6 cycles, 30 KSI, and it's just going to stay there. And it just flattens out. It doesn't matter how many cycles you run. It's going to be set there. And so this is our creep part of permanent set.